Well, hello, friends. Today, we're going to work on a new tool for performance analysis, and it's going to be a profiler. Because very often when I'm working on Serenity, I find something running kind of slow, and it's very, very limited what I can do to figure out what is going on. And a typical thing is that I do is that I look at the stacks in the system monitor. So if we bring this up here and then I go to the happy birthday page for Serenity on the website, then I can see that there is CPU activity happening here in the protocol server, for instance. And I can switch to it and I can see that there's some stuff going on, but it's only like updating once a second. And I can kind of catch a glimpse of the stacks that are happening, but I don't really come away from this unless it's doing like exactly the same thing over and over. I don't really come away from this feeling like, okay, I see what's going on, right? It would be much better if we had a more proper profiler, which would collect stacks regularly and then allow us to see like which stack is the most commonly occurring one, basically. So, and you know, like all the usual profiler visualizations that we can do. But the important thing is that we need to collect stacks. And currently, we don't have a way to do that. So I'm thinking we're going to have some kind of way to put a thread into profiling mode. And while it is in that mode, we'll just regularly capture its stack. I think maybe the easiest thing to do is to just do it every time that we preempt it. We can gather. We just look at what is the current stack when we interrupt it to schedule another process or another thread, and then we'll just save that somewhere in case that thread is being profiled. So I think that makes sense, but I haven't really thought about it any more than this. So we'll just start and see what we can come up with. Here is the thread class. And I think we'll just add something like, you know, bool being profiling enabled. Is profiling enabled? Maybe set is profiling and set profiling. Yeah, that's good enough for me. So void set profiling. And I think this can actually just be this simple. Of course, I don't know yet where we're going to store all of this stuff that we gather, but we'll find a way. Profiling, and we'll put that bool down here somewhere, wherever. Not the most important. Okay, so now threads can be in a profiling state, which they are not by default. And then I guess we should have a way. Maybe this should be per process, actually. I was thinking first it should be per thread, but now I'm thinking maybe let's do this per process. Yeah, but we can save those getters and setters. I'll just take these, bring them over to the process, because usually you want to know what a process is doing, not just a single thread. A single thread is kind of a special scenario. Might become relevant later, but process private. Where are you? Cluster of bools. Is there no cluster of bools in process? Oh, here they are. Not so many, actually. Okay, so now we're going to need I guess, some kind of a syscall to enable profiling of a PID and disable profiling of a PID. So I think we'll just make a little syscall for that. Maybe profiling enable PID. Disable. That's nice. Syscall. One thing that's nice is that everything doesn't always have to be perfect in the first iteration. That's something I see some people kind of misunderstand, I guess, about this system, that it doesn't have to be the perfect, correct way from every time that I implement something new. It's like, it's okay if we eventually want to have something like dtrace or whatever, but right now we just build a simple stack collecting profiler because it's just steps, small steps leading somewhere, little by little. I think it's very dangerous to get into the mindset that you have to do everything correctly or like everything has to be perfect before you can move forward. You got to be willing to move forward with something that's not perfect. Okay, so now we have those syscalls. I guess we can maybe add them here. Profiling enable. Okay, and they'll just be very simple. Something like that. Disable. All right, here we are. Now what's going to happen when we call these? We'll end up in process sys profiling enable for PID or profiling disable for PID, and I guess we'll just do some simple thing like we'll disable interrupt so we can look at the process table. Process from PID, if no process, return no such process. Otherwise, if is superuser, if not superuser, and process UID is not my UID, forget about it, bro. eperm. Otherwise, process set profiling true. Okay, and disabling profiling is going to be very, very similar to that, except false. Okay, so now when we preempt a process, meaning that the scheduler gets a timer tick, so the timer wakes up the CPU and says, hey, time to interrupt the currently running process and schedule something else to run instead. Then we are here in the scheduler timer tick. And this function here specifically is what causes that. We will decrement one from the currently running thread's number of ticks left. But I think we're not just going to do that, but we're also going to first look at if we are profiling the process that the current thread is in. If so, we're just going to get his stack and put it somewhere. I don't know where yet. We'll have to figure that out. But let's see. If current process is profiling, where do we put this? We don't want to put it in the memory space of the process being profiled because that will interfere with the process. So we should probably have his dedicated allocation for this. Now the easiest thing to do right now is to just get the backtrace for the current thread. I think maybe we can maybe we can just call that. Although it's not really safe to do that while we are handling a timer tick. because this might look at the, this will try to symbolicate the stack. So we'll try to figure out all of the names of the different functions on the stack. And we can't do that here because when we are handling a timer tick, the CPU interrupts are disabled. So that's not going to work. Because symbolicating might need to load the symbols from the program binary, and that would require interacting with the disk and stuff like that. So we are just gonna not do this usual thing, but instead we'll need some way of storing the backtrace. And the backtrace is gonna be it's just a bunch of pointers, really, like from the current stack base pointer to the like the lowest thing on the stack that we can find. So it's a vector of 32-bit values, essentially. So what did I say? Stack is current get maybe like a stack trace. What did we call it? Back trace. Call it like a raw backtrace. Stack maybe. Okay, and then we have to put this somewhere. Maybe the easiest thing is to just have a big allocation somewhere where we put these. So if we have a maximum stack size, we can just make an array. I guess that would be okay. So let's see, let's make a profiling buffer or something like that in the kernel. So when we boot up, let's say that we allocate a megabyte for that. And then it can just be like, I don't know, like it's 4 bytes per stack frame, and say that we allow up to 100 frames in the stack, and we just divide a megabyte by that. That will give us 2,600 and something samples. That's not super great. What if we only allowed 30? Yeah, it's getting closer, because if we interrupt it that often, but of course other stuff is going to run too. I'm just thinking the kernel runs the timer at 1 millisecond it wakes up every 1 millisecond. So if there's only one process running, we will record 1,000 samples per second. That means that if we have 30 frames per sample, we will be able to record for 8.7 seconds until we start overwriting parts of the buffer. But maybe that's okay. Let's just say that it's okay for now. So say profiling buffer, maybe we'll make it global for this. Kbuffer. Something like this. G profiling buffer is kbuffer. Create with size 1 megabito. Maybe we can even do it that way. Booyah. Okay. And then we'll also need to have some kind of profiling. This probably should be in some kind of a class namespace or something. Let's not be gross here. Profiling. Profiler. profiling.h. Okay. Let's not be gross. Okay, kernel profiling. So we need optional, kernel k buffer, namespace, profiling, static void initialize. Oh, just void actually. And oh, this can be out of line. Okay, and then we will just have a way to get to the buffer. How are we going to expose this? We'll do something like a struct stack profiling stack, and this will have U32 frames, and we'll have 20 frames or whatever, and this will be one stack. And then we'll have a way to give you a stack buffer, so like stack buffer. Or maybe it should give you like the next place to write your stack. So next stack slot, and then you will write to that. Okay, I think that's okay. And then maybe we'll also make a dump function so that we can dump whatever is in the profiler. This is going to be a little bit hackish, but it's just to get something going. Process. So we can say when we disable profiling, we will profiling dump. All right. Profiling. In fact, maybe when we turn on profiling for the first time, that's when we should initialize profiling. So we'll do this, initialize if needed. This is kind of cool. We don't need to do it on startup. Because why should you pay for profiling if you're not profiling anything, huh? You know it makes sense. Okay, so initialize if needed. If no gprofiling buffer exists, I guess if it doesn't have a value, right? And do that. Make it compilation unit local. All right, now we need something for the next stack slot. So that's going to be just compute how many stack slots we do have. So slot count. Next slot index. So here we'll just say s slot count 0 as next slot index 0. Okay. So now the next stack slot is going to be slot with an stack slot with an index s next slot index plus plus, something like that. Next stack slot with an index, and that is going to be return stack S profiling buffer data value.data. My bad. Wait, shit. We want to do this and then index into it. Right. Okay, and then return slot, because if S next slot index is exceeding the slot count, then S next slot index is 0. We wrap around, and the count is gonna be the profiling buffer value size divided by size of stack. Okay, now how do we dump one of these finally? Well, we will just say I guess we can dump from 0 to the current. That would make sense. So for size t 0. This is definitely not perfect, but it'll do okay. I think maybe we're going to grow this thing up to like 16 megabytes or something, or 8, just something way bigger so that we can record more, because if we're doing this, then it's okay to spend memory. We want to learn about this. It's probably okay to use 64 megabytes too. It's just, have to say some number. So stack with index I, and for the stack we'll do like 4 j 0 j is frame size, or frames per stack. Size, frame count, const size t frame count. Max frame count 20. Let's go with 30 then, since we bumped the megabytes anyway. Max frame count. A little bit of space, and then maybe we put the number like this just to be cool. And actually, let's use debug printf for this. Stack. Why is this so difficult? I. Zoo. 2 zoo. Let's see. And we show it like hex pointer like that. Okay. So J, and then stack slot J dot frames. No, stack slot I dot frames J. Stack is stack slot I. K. I wonder if this will be remotely understandable what's happening here. We're going to need some user space program to toggle this. Space profile? Profile. Profile. That's kind of weird. Is that a thing? Profile? Okay, well, whatever. Profile's good with me. That's not what I meant to do at all. I meant to do this. Okay, and then we need to include this in the kernel. Profiling.o. There we go. And of course, userland is going to have a profile.cpp. Stdio. Okay, now we are going to get a PID and a flag here. So I guess I can type these out. Dang it. If argv argc is not 2, 3. We need 3. Then printf usage profile PID on off, something like that. Okay, and then PID-T is A2I argv1. What's A2I from? Is that stdlib, maybe? Yeah, okay. And then pull on or what do we call it? Enabled is strcomp argv2 on. This is some old school style of programming right here. If not enabled. Profiling disabled. Good. Okay, and then if we get an error, we can just, oh, frick. We don't know which call we were making, so we gotta take care of that. If this does that, error, profiling enable. Zero. This was, why did I make it so difficult for myself? Oh, I guess we'll just do a full rebuild so we get syscall wrapper and libc as well. We're still not getting that raw backtrace somehow. So how do we get that? Get a raw backtrace. We have backtrace impl. I think raw backtrace const. How do we do this? This is essentially this function right here, except no symbolication. So raw backtrace is just going to give us a vector of u32s. And we don't need to recognize the symbols. We don't need to create any strings. all we need to do is remember the U32s that we've seen. So here we'll do just a backtrace, and then backtrace, wait, backtrace dot append ret adder. No symbol allocation needed, and just return backtrace. Actually, it's a bit weird that we don't include the frame putter, so I think we'll just start by adding the frame putter to it. Backtrace dot append. What is the frame putter? It's a U32. Oh, wow. Cool. Raw backtrace, scheduler. So, okay, so now we get the raw backtrace. Then we got talk to the profiler. Next stack slot. We gotta fill this guy in right now. So I max of stack size. We'll call this backtrace, I think. Otherwise, it's gonna get a little confusing here. So max of backtrace size and profiling max frame count. Slot frames I is backtrace I. Okay. Will this work? I wonder. This super did not work. Okay. We crashed in at exit. So I think we did something here that's sets up an exit time destructor, and that's not cool. So we gotta avoid that. We'll just do it this way. And then because optional has a destructor, can't use that. But we can do this. Hey, what does this give us? Create with size. Dot impl. Can we please leak this somehow? How the heck do I leak it? Kbuffer. Can I leak the buffer, please? Okay. We are leaking it. Great. Right now, there will be no way to clean up if you make a mess. So, profile and buffer size. Great. And this has to be kbuffer impl. This is still not good enough? Wait, why? Init CVP 210. Why are we getting here at exit? Who is calling us? We must have set something up that generates an exit time destructor. But who would do such a thing? Profiling.h. I set this thing right here. I guess not. I guess this is probably something obvious that is just not obvious to me at the moment. Which one of you jerks is doing this to me? Let's just do that. What if these are just empty? Why would any of this... I don't understand. Okay. I'm paranoid about this thing now. Struct stack. Okay, what is my stupid problem I'm having? Okay. Why do I have blindness to what I've done? Can I get a backtrace for that? Init to 10. What if we just skip over it? Who cares? But we're setting up an exit time destructor. Why? Why are we doing this? Illegal instruction. Yeah, that's the point. This is not the problem I thought I would be having. Does this still happen if I explicitly initialize all these things? Yes, it does. Wait, do I have a static in some function somewhere? Just make less code. Okay. Today it's apparently one of those days when I am too tired to brain, but I still want to move forward. So I have to overcome this. It's this thing right here. Oh! Totally forgot about that thing. Okay. Oh, frustrating problem right there. Okay, so this problem is in init CBP. We forgot about this guy right here. He has an exit time destructor. Goodbye, guy. Damn, should have looked at the div. Well, anyways, now that I've blamed being tired, let's get back to business. So, what can we profile here? I guess maybe the menu applet that does this thing because it's always doing something. So he's PID 7, profile 7 on. And we died right away. And Wonder why we died. We're doing... okay, so we're interrupting him. We're in the timer tick, and then an assertion fails very soon in the timer tick function. Timer tick. So, oh, should be min. We should copy the whichever is less, like either the backstraight size or the maximum frame count. That's a silly mistake. Profile 7 on. And this is looking okay, and then let's turn it off. And these are all of our stacks. Look at that. Now, I wonder if these stacks are actually useful. It's hard to say. This looks like a legit stack right here. It's a bunch of user space symbols. This one looks like garbage. A lot of these look like garbage, actually. This is a kernel address, and these are kernel symbols. Kind of interesting. So it's hard to make sense of these if we can't run them against the symbolication code. So we're going to have to symbolicate these things. So there needs to be a way to get this data. Maybe when we dump, we can actually, we should remember which binary we are profiling. So let's see, profiler, profiling enable. Let's see, profiling. Let's do reset. Okay, so when we reset, if we don't have a buffer, we'll allocate one, but we'll always set the slot to 0 again, so that we start over, because then we can also remember the name of the... I'm thinking we're going to remember the file name that we are profiling, or the executable, I guess. What do we have when we start this? So profiling enable. We have the process. Let's start process executable. Yeah, there we go. Can give it the process executable. Okay, and then profiling stop. Stop. Okay. I don't know. We are discovering this, how this can work. Okay, so now we'll take the executable, and then I think we're gonna stash that somewhere. So like custody, yes, executable, kernel, file system, custody. So when you start profiling with a custody, I will say if executable, or actually we'll do it this way. If executable, then ref it. And we will also have a stop where we will do the opposite. Null putter, and then we'll dump before we lose the executable, because dumping now we'll be able to look at the contents of the executable. Actually, maybe the best thing would be if we would just give it our L floater, now that I think about it. Symbolicate, because we have ksymbolicate, we have backtrace. We have this code right here. We should probably just take this and write it so that it can operate on this stuff. So maybe the thing that we should start is, we should start on a process. This will make a bit more sense. Okay, and then, let's see. So we'll remember the process. And then this won't make sense. Process, process. String. Make backtrace. And the process is sProcess. String builder. And we are just going to take a stack here. So stack. We don't need to walk the stack. We have the stack. So let's append stack frames 0. Frames I, symbolicate stack frames I. Okay, and this thing just needs to walk from size ti to stack max frame count if stack frames I is 0, then break. Okay. Where's the mangle? Actmangle.h. Right. Demangle. So then here we will just dump the, instead of dumping the whole raw stack, we will say debug printf. Make backtrace stack dot characters. Okay, and maybe we'll do a little bit of indentation here just to be cool, just to be nice. Process L floater. Oh shit, we need the process definition for that. Process libelf elf loader. Okay, do we have everything? I think we do. Right, forgot to change the API. Start process. Don't need optional, don't need kbuffer. And okay, now here we just have to say this. Cool. things I'm forgetting. Okay, so these are the stacks we got. They look a bit crap. But this one looks rightish. At least the start of it. Or what is really going on here? We're interrupting. Are we really interrupting? What process is this? 7. That's the CPU graph. We'll try again. Okay, now it's sorting stuff. What is this? I wonder why the stacks are crappy every time that we catch it. What happens if we cat proc 7 stack? See, this is what I was expecting to see every time, basically. Because this is what it's doing much of the time. Of course, we are sampling whenever whenever it's running is when we are sampling. I guess what we should really be doing is, I mean, there are two different schools of profiler, right? There's the sample the process whenever it's running school, and then there's the sample the process at a regular interval school. Now, if you sample it whenever it's running, you get you learn what it's doing while it's busy, right? Like you learn what he's spending his CPU on, but you don't learn what he's doing when he's just blocked. So if a process is blocked half the time, you're not going to learn that if you only sample while it is running. But if you are just looking to optimize CPU usage of a process, then looking at why it's what it's doing when it's running, it's usually what you want to do. So there are pros and cons to both, really, because the one where you see the blocked stacks as well can be a bit muddier to read. But why don't our stacks look like this? What is going on when we interrupt this guy? What happens in the timer tick, really? I guess when we call the timer tick, then we have a register dump here. So actually, it isn't quite right to ask for a backtrace based on the stored frame pointer of the thread, because this is old. We want to use the frame pointer that we actually had exactly when we interrupted the thread. And we have that. So we're going to tweak this here to be based on something. We'll be based on the current stack base pointer. I think this will give us better stacks. We'll say frame putter, or yeah, or let's just call it EBP because it's more clear what that is anyway. So add EBP, and then we'll walk from EBP backwards in the process namespace or process address space. Raw backtrace U32 EBP. All right. All right. What did we get? Crash. Shit. Okay. What went wrong? Can't find user region for this address. We're trying to read from some, what is this, some deleted memory in the kernel? That's not good, bruh. I'm messing that up. Raw backtrace. Well, is this a symbolication code? Make backtrace. Okay, so let's dump the raw stacks that we got before we dump the whole backtrace. So we'll say like raw stack. Symbolicated stack. Sync and run. All right. I have to sync here because the active syncing updates the kernel symbol table. If it don't sync, then it's going to look really wrong anyway. Okay, so this is our raw stack. I think it looks pretty cool. So why do we, I mean, this looks actually really great. So what's wrong with this? Enter process paging scope. We can't do that. Process is still there, still running. Make backtrace fails. Make backtrace. Who calls that? Right here. So make backtrace tries to go through this backtrace right here, and then it somehow screws that up. But why? I mean, actually, we know that it already fails an enter process paging scope. So why does that fail? Let's print out something while we're trying to do that. So entering paging scope of process. Oh, hold on. Sys profiling disable. Aha! This is wrong. I don't want to start profiling of the process that calls profiling enable. I want to start profiling the process that we found, the one that we actually want to profile. That's why it's failing, because the profile command has exited. And then we try to enter the paging scope of this exited process. Umount. Okay, this should be better. Okay, now we're gathering stacks, and then say that we are done. And look at this. We have the stacks. Here's a raw one. And we can see, dude, this is so cool. It's definitely in the process statistics reader get all. This is what it's doing most of the time. The little applet is just opening proc all and then parsing that and then turning that into a CPU graph. Because proc all is this file that has all of the different statistics about every process and thread in the system. So this is going to be super awesome. Profiling Okay, so let's stop making the raw stacks once again. Yeah. Okay, and let's profile something else. What would be interesting? Why not system monitor? Although it's also going to be doing the proc all. But at the same time, maybe that's interesting. Profile. System monitor is PID. What is it? 16? On. And it's not particularly heavy to do this, I feel like. I mean, the system still carries on. We stop it and look at all of these gorgeous stacks. So sometimes the first frame is just some nonsense. But I guess that's maybe okay. Maybe we should ignore the first frame of these stacks. Because, probably we can. Very, very cool. Yeah, let's ignore the first frame of these stacks. So make backtrace. We will just skip over it. And oh shit, there we should remove that little log there. Okay. And let's see what Windows Server is doing, right? So profile 10 on. Now I'm moving the window, so Windows Server has to do some stuff. Turn off profiling. We collected 288 stacks, meaning that Windows Server has been interrupted 288 times. And so it ran for effectively 288 milliseconds. You know, roughly, anyway. God damn, this is going to be so useful. Now we can actually see what everyone's doing. Finally. Should have done this sooner. I've been so frustrated that I could never see what everyone's doing. Of course, we're going to need some tool to combine all of this into a graph or a tree of some type. But that'll be a separate project. Right now, we are just trying to generate the data. So, damn, this is so interesting. Let's try it out on the browser, because I've been wondering what the browser is doing when I'm opening that happy first birthday page. So, or actually, I'm wondering what the protocol server is doing, because he's the one who usually sucks up all the CPU. So let's just start profiling him. So profile 20 on. And just to see, yeah, you can see him sucking up the CPU. And maybe this is very, very interfering. I'm not sure. Seems like he's not able to load the resource at all. What if we turn off the profiling? Good gosh. These are some pretty big stack traces that we recorded. So what are you doing all this time? Sending outgoing packets. Oh, wait a moment. That's what it's doing all the time? TCP sockets send outgoing packets? What the actual frick? This shouldn't be CPU heavy. Connect, sysconnect. So what is this? Damn, I mean, this is just so extremely interesting. So it seems like it just hangs doing this. Well, I don't know why that is, but that is extremely interesting. So I'm guessing that's definitely, probably, super definitely, maybe a bug in the TCP implementation that we need to look at. This just opens up so much stuff that I want to look into, but I can't look at everything at the same time. So let's just work on the profiling code a little bit more instead and see if we can clean some things up. So what do we have so far? I mean, this is kind of a mess, right? This is not very clean or anything like that, but at the same time, maybe this will do us well enough. I'm kind of thinking that we don't need to get fancy. We don't need to have multiple profiles running at the same time. Like, if the system only allows you to profile one process at the same time, I think that's okay. One thing right now that would totally mess everything up is if you have multiple threads in a process, then we will just interleave the stacks. So we're going to have to store some more info about each sample. So we should probably rename this here to sample. Sample, oops. Okay, and what do we call this? Oh, frames is fine, but we should have like a PID PID. Int. Let's just have int PID int TID. And maybe we'll store the when this sample was taken. So timestamp, something like that, and then this can be the next sample slot. Okay, so next sample slot, blah blah blah. So in the timer tick, we want to, let's see, we can call this sample now. That's fine. And then we'll store the frames, and then we'll also store the PID is current PID sample TID is current TID sample dot timestamp is G uptime. This is monotonically incrementing clock that we actually, you can see it being incremented right here. So it increments every time there's a timer tick. This will tell us exactly when this sample was taken, which will make it possible to you can plot these samples. If you have all of them, you can know that these two samples were actually like 100 milliseconds apart or whatever. If you wanted to show that. Let's see, so let's rename this a little bit and call it like stack max stack size, max stack frame count. Yeah, 40 is pretty good. Now the size of this guy is 136. Booshy dooshy. So 136. We still can record in 1 megabyte. In 1 megabyte, we can record 7.7 seconds. So in 8 megabytes, we can record almost a minute. That's a lot of time. So we should be good, quite good, because we're never going to record for that long anyway. in practice, at least not anytime soon, I think. Most of this is going to be like, record the weird thing for a few seconds while it's hung or while it seems very busy, and then get the data out and look at it. So what else can we do to improve this situation? I guess it would be nice if this didn't just come out on the debugger, right? But you could actually read the profile stacks from somewhere. So I think we're going to expose them through the procfs. Is probably the easiest. So the absolute coolest would be if you got this big JSON out of this whole thing, right? Just think we'll do that. So we'll put it in the root, like profile, something like that. Will just be proc profile. You can cat this and we'll give you a JSON dump of the last profile you took. It's very simple, but I feel like this is going to be so freaking awesome. Procfs profile. Okay, now we gotta make this happen. Okay, wait, I'm just gonna steal some boilerplate here. Booyah. Okay, so the profile is gonna be a JSON object that has a little bit of fluff first. How do we start one of these? I forget how you do this when you haven't object as the outermost thing. Why do I forget how everything works? I guess we just do it. Pick one like this. Builder. It's ambiguous. JSON object serializer. Takes a builder, has a template argument. All right, well, okay, buffer builder. Do I do this somewhere? Oh, I do this somewhere. Okay, so it's this simple. Just do that. Maybe we'll call profiling to take care of this for us. Or actually, kernel profiling. I know how we're going to do this. We're going to have something like first thing is that profiling definitely have to stop the world for this, otherwise things are going to get really weird if we interrupt ourselves here. So this is profile. Don't need that. And PID. Profiling PID. JSON add array, and then the name of the array. It's going to be samples for each sample. This is how we'll do it. Auto sample array dot add. Then we just add a value, which I guess we want to have the pointer address and the name of the function there. So profiling. How do we do this in a nice way? guess when we have for each sample, we'll do something like this, sample, and we'll also give you a string with symbolicated version, because why not? Callback, or maybe something like that. This is not going to be particularly fast, but it doesn't matter. This is something that you do after you recorded your profile, right? So it's not performance critical, I think. And then we also needed PID. Yeah. Profiling. Okay, now how the frick do we do this? PID is easy. SPID. Process PID. Okay. Maybe we'll actually rename this to last recorded PID. Okay. And frick, actually we can't. We're not going to be able to make the backtrace if that process dies. So this will only work while it's still running. Maybe that's okay. Or should we go through and symbolicate? Maybe we should go through and symbolicate and then store all of it. I don't know what's best, really. Right now, we can say that it only works if the process is still running, for the moment. Okay, so for auto. No, not for auto. This is how we iterate all of the stacks. Sample, and each sample has PID, TID, timestamp, and frames. Oh, actually, yeah, so I didn't need the last recorded PID. I don't know what I was thinking with that. And here we can have a string. Oh no. The string would need to be U32. This is kind of annoying, because this like ends up taking up a lot of space, but at the same time, let's just do it this way. It simplifies programming right now, and then we have some optimization opportunities in the future to fit more samples. Okay, so here what we're just going to do is we're just going to say sample stack slot should be called sample slot. Sample slot or sample dot symbolicated frames. Wait, how was this working before? I already forget. Make backtrace. Oh, that's how we're doing it. Maybe it's easy enough to do it as a string. It's kind of lazy, but maybe that will work. It's not perfect. Be better if we had it not just as a string, but as proper data. So for each sample, why is my brain slow again? Speed up, brain. Instead of this doing that, we will write the symbolications into the thingy, into the sample. Okay, so we're going to make a new builder, and then no new lines, or actually no builder needed either. We'll say stack symbolicated frames I. Frame index, let's say. Frame index. Okay. I offset it because of the offset here. Okay, and then I mean, actually, did we even need to do that? We didn't need to do any of that. Don't need the frame index up here, and this one can do this though. So we'll just keep a running counter. As going to be, and this is a string, and we're going to store what exactly? Symbol string slot is that. Okay, and then here we'll just do symbol string slot is string format. And we just want the name. Here we can't produce a name, so we'll just have no name, empty string maybe. And likewise here, can't produce a string, so empty. And I think we can do it like that maybe. We could optionally here have an offset or something. I don't know. Maybe this is okay for now. So when we stop, we want to. Wait, what exactly are we doing? Symbolicating it, right? Okay, don't need you. OU. Okay, and then callback sample. Don't need the dump function. Stop, we'll just put stop further down here, and this will take over what dump was doing, like that. Okay. Okay, and then in procfs, we don't have the PID like that, and we can actually just do a simple array serialization after all. So all of my screwing around there was pointless. Array serializer. Array. Hooray! Array. Array add. We want to add a JSON object at this point, so add object. Okay, and then when we're finished with this, array.finish, return builder to build, I guess. Okay, and then here we add the PID, which is going to be the sample.pid. PID, TID, samples, For auto. For size T. Hi. 0. Hi. Profiling. Next. Stack frame count. If sample dot frames by 0 break. Sample array finish. Okay. And then here we add PID. Or no. No. It's the frames. Damn it. Address. This is a U32, I guess. There's no such thing. What can we add here? Strings. We'll just maybe do it like JSON value. I would like it to be a JSON value. Is that not going to work? Oh wait, I can't give it a name because it needs to be, samples need to be objects. Dang it. Right. Frame object. Here we go. It's a little bit tricky how to do these. Frame object, add. Frame object, add. Symbol. That's not a U32, it's a string. Frame object finish. Okay. Oh, didn't quite get it. See if I got it right. Nah. Crashed in the JSON parser. I guess I didn't do very well for JSON. Bad enough that the terminal crashes also. Shit. Guess that must have been very, very bad. Oh, I see the problem. Symbolicated frames. This is just a random string object, and we can't be passing that, I think, like that. We have to actually well, one thing is that we never actually cleared those. We should have made those null at some point. Profiling CPP. Those strings, because we didn't new those, we just allocated them like this, right? So the constructor never ran. So how can we do that the most easily? It's a little bit annoying. All of those strings. I wonder if this is containing garbage, by the way. It shouldn't contain garbage. but that's a whole other issue. I think it should be 0. How do we know if it's 0 initialized? If they could 0 fill on demand. Well, they can, but I think they will 0 fill on demand. There's no reason that they shouldn't. So why would we have garbage in the string? We definitely have garbage in our string here. So, come on, Andreas. I really hate the situation I put myself in with these allocated here without running any kind of constructor. So, I mean, it's okay because the string object is just 0 initialized anyway. I just don't like that I put myself into this very ambiguous space. But I feel like it should be fine. So maybe I'm like dumbing something here. Characters. What if we just do that? No, still screwy. Yeah, of course. Dang it. Okay, what would be the laziest way to get out of this situation? Stirred up. Can use stirred up. Sample. Symbolicated frames. I guess we could use stirred ups. So here we'll just say in the symbol string slot, where is it? Right here. Wait, why can't you store that? Assigning to char from a const char. Okay, so stir dupe. Okay. For empty, we can just do that. That's okay. Stir dupe. Dot characters. It's very gross, but it is what it is. Procfest. This is by no means final anyway, so it's not like it matters that much. Just want to get something working, please. So I guess if we should have there should always be something available in the string. If we have a frame, then if we have a frame address, then we should have a frame symbol. I guess we can't do this, so fine. We'll do something horrible like that. Or actually, let's just be awful. Const cast. Ah. You're not the boss of me, GCC. Okay, cat proc profile. Still garbage. I still put garbage in there. So why do we put garbage then? Because then I don't quite know why we're putting garbage. Printf. I put string. Something like that. symbol string slot. Okay, 1 k printf. Okay, 2. What's going on? What are we actually putting in this thing? Okay, we're putting complete crap. These look like phone numbers. Not to anybody I know, but still. Okay, so now we're just putting crap there. That's a little bit surprising. What are we doing? Oh, God, I'm so stupid. Okay. See, I removed some things that were here before, but I didn't remove the argument corresponding to that. Ugh. Okay, let's backtrack to where things were not so doopy. I can't go back that far. Okay, well. God damn. All right. Okay, that was a dumb problem. One that could have been totally avoided. But we didn't avoid it, so it is what it is. Empty. Isn't it nice when you realize that everything is your fault? That. Two. Okay. Wait, what? Profiling 64. Else. Wait, what's wrong here? Oh, it was fine. Okay. This is more like it. Look at this absolutely magical output. Now we're just missing the timestamp. We can put that too. So procfs timestamp. Okay, so PS. Who are we curious about? How about audio server? PID 12. Profile 12 on. Maybe that's enough profile? Okay, so what did we learn? Proc, profile. Shit. Nothing. Why did that happen? Audio server. Were you not doing anything? Oh, now we got some stuff. Okay. Well, I don't know what was wrong that first time. We have the timestamp here. That's in milliseconds since boot, I guess, which is pretty cool. So, oh, this is, the TID is wrong. Sample TID. So, audio server has 2 threads, which makes it interesting to look at here. So, profile 12 on. Proc profile. So obviously this JSON format is not super pleasant to look at like this. Also, we have new lines here which look totally off. Profiling, so that right there. Fixing things up, it's getting nicer. So obviously this JSON format is not how you want to look at the profiling data in practice when you're actually working with this, but I think it will be very good input to profile whatever we end up building. So why doesn't it capture something? That's kind of weird. Maybe it never gets preempted. Just wakes up, gets scheduled, but never preempted. So that's an interesting issue. Because normally audio server would just wake up and go to sleep. So we can see it's thread number 1. Wakes up, does a little bit of stuff in the mixing thread. Basically, he just wakes up, looks if there's something to mix, and then goes back to sleep. It's so sweet that you can see the kernel, what's happening in the kernel here as well. Not just user space. Very cool. It's a large number. Why is this number so large? Okay. Well, I guess that's fine, whatever. What is that number? I'm suddenly so suspicious of this number. Okay. I guess that's a number that we have in the kernel. Wait, are these maybe off by 1 now? Something here doesn't add up. Is it this thing that I did, where we skip over the first one? Stack frames. Recognized symbols. Okay, so we should start at 1 here as well. Otherwise, things get all goofy. Okay, so that's a good thing that we caught that, because that was not right. What else can we look at? Let's do Windows Server again. I like him. And on. We'll do some changing the opacity here with the wheel. Oof. And oh, it took quite some time there to, I guess, save all the strings. Yep. So the process that the profile command ends up paying for doing all of the symbolication, because it actually happens in his process context. Or like accounting-wise, he's the one who pays the CPU time for the kernel doing all the symbolication. We could do symbolication in user space, but that's another issue that we can think about later. So what's going on here? This is pretty neat. Blit. It's very user space heavy. Programs constantly being interrupted in user space. compositing. So cool. Look, we interrupted him when he's doing an MMX optimized memcopy. All right, okay, I'm getting carried away again where I just want to look at profiles of everything. So let's commit what we've built here, and then we can continue on it, some other day. But I'm gonna have to wrap it up now because I'm running a little low on time here. So, kernel. Implement a simple process profiler, process time profiler. You can now, kernel now supports a simple profiling of all the threads in a process. Basic profiling of all threads in a process by calling profile. What did we call this syscall again? Profiling enable. Finish the profiling by calling profiling disable. Pity. A simple bin profile command is included here that can be used to initiate, start, stop profiling, like so. Okay, that's kind of nice. After a profile has been recorded, it can be fetched from proc profile. There are various hard limits on this mechanism at the moment. Only one profile. Only one process can be profiled at a time. Can only allocate up to we allocate 8 megabytes for the samples. If you use more space, things will not work and probably break a bit. Things will probably fall apart if the profiled process dies. Probably fall apart during profiling or while extracting proc profile. Limits, AK bugs, various limits, or bugs. This all works by recording the current thread stack whenever the timer interrupt, whenever the timer tick interrupts a thread. Timer interrupt happens. Recording thread stacks whenever a thread in a profiled in a damn it, why can't I fit this on the line? Recording thread stacks when the timer interrupt fires and the currently executing thread is in a process being profiled. 73 characters. And the current thread is in a process being profiled. Note that symbolication is deferred until profiling disable, since to avoid adding more noise than necessary to the profile. Okay, so I think that's pretty good. Of course, this is just a start, but it's a good start, and I thought it would be fun to do some DevTools hacking that wasn't just about the IDE, but also building like another kind of dev tool. So ultimately, you know, in the perfect, beautiful future, I would like to have a profiler that can work together with Hack Studio, or maybe even be integrated, but probably not integrated, but running as a helper for it. But you know, we're still some time away from that type of stuff. But this has been some really awesome progress still. So let's profile the taskbar on, and I will just hover over these guys right here and go off. Proc profile. Maybe let's maximize before we do that. Oh, JP proc profile. Boom. So what is happening? This is the taskbar process. I guess it's sending some message to the Windows server to update the window. What are we doing here? Painting a label. Ah. It's so cool. Oh, this is so cool. Can you tell that I'm excited about this feature? And it's going to be even better when we build a UI for it. But not today, because we are done for the day. So if you made it this far, then I thank you for watching and for hanging out while I implement the foundation of a time profiler for Serenity OS. Thank you very much for hanging out. Seriously, I hope that you saw something interesting. Did I say that already? And yeah, things are going pretty okay with this project so far. A lot of new supporters on GitHub, sponsors, and Patreon lately, so thank you everyone, and welcome to the program. And a lot of new subscribers, welcome to the channel. And you know, just a lot of new people. It's lovely to see all the new people coming in and taking an interest and hearing all of the reasons that this speaks to you is very fascinating. So I'm glad to have you all here, and we're almost at the end of the year. I don't know if that means anything to anyone, but Christmas is coming up, so I'm in a good mood, and I'm going to stop talking now. So thanks for hanging out, and I'll see you next time. Bye.